Hey, my name is Skoglund. I'm from the Open Codecs team in Chrome, and today I'll talk about some recent work in low bitrate speech compression, also known as speech coding, where we're using deep learning. What is speech coding? It's basically data compression of speech signals. A bunch of parameters or features are extracted from the input speech waveform. Then they're quantized into a digital bit stream for transmission over a channel or for storage. And at the receiving side, these features are decoded to generate output speech waveform. And a device that is used for speech coding is often called a speech coder or a speech codec. I'll be using both terms. Is there a need for coding speech at low rates these days? You might think, with the internet boom, that bandwidth is not a problem anymore. That's not the case, though. There are areas of the world where the digital infrastructure is pretty bad. For example, 1.5 billion of the mobile subscribers in the world are still on 2G cellular networks. And there are about 1.5 billion more on 3G networks. That's pretty low data rate. And furthermore, many of these so-called unlimited data plans, they are not unlimited because if you exceed a certain number of gigabytes, they will throttle and you'll end up with a pretty low data rate. And another thing nowadays is that in urban areas, all due to the heavy usage of internet, it will put an enormous burden on the networks, and you will get flaky connections, even inside cities, with dropouts and low throughputs. So there is a need, indeed. The question that kind of pops up is how few bits can we send by still having a good call? And let's look at a theoretical lower limit. If we take input speech audio and use speech recognition to extract what text it is, and maybe put some prosody, that means intonation and other things like that, and who's speaking, detect some emotion, and send over this information. And at the decoding side, we then have a text-to-speech synthesizer that can produce these output speech from these input parameters. How few bits do we need for this in a lower limit? In the 50s, people tried to estimate this. The most well-known approach was taken by Shannon. He used a lexical approach for written English and estimated around 50 bits per second. What's all that required? Another approach was looking more at the acoustical waveform itself and ended up a little bit higher, 1600 bits per second. The topic of this kind of estimate was revisited quite recently, and they ended up with a rate for general speech at around 100 of bits per second. So theoretically, we can go very low. We can probably go away with just a few hundreds of bits per second. There is a big catch, though. All these limits, they require a long delay, or actually infinite delay. So it's not very practical. Speech coding has been used in practical applications for a long time. And it has kind of crystallized out to two basic classes of coders. The first class are the parametric coders, also known traditionally as vocoders. These coders are based on a speech generating model, and they extract features to control a synthesis model. By this kind of mechanism, they can go very low in bitrate, with rates from around 300 bits per second up to around 5 kilobits per second. The key problem is that these systems are completely determined by the model for speech production. So it doesn't really matter how many bits we give to the model in the end. It will still sound the same. And therefore, these systems have mostly been used for, and still are used actually, for bandwidth constraint scenarios, such as secure communication, and typically using narrowband speech sampled at 8 kilohertz. The other class of coders are the waveform or waveform matching coders. They are typically operating from 3 kilobits up to hundreds of kilobits. They have no limits in the quality because they don't rely on a model in such a sense. The more bits you give them, the more they resemble the actual waveform. So an infinite rate obtains infinite quality or infinite fidelity. These codecs are very versatile, so they can be used for different types of signals. They are used in narrowband speech, wideband speech, and fullband. They're also even used in most stereo and spatial audio codecs. The problem is that they break down for very low rates, and that's why parametric coders are still used for these low-rate applications. Let's look at how speech coders are used in typical internet calling or conference system like Zoom. Typical rates are around 16 to 32 kilobits per second, and that's wideband speech. The codecs that are used are always waveform matching coders. But as I said in the prior slide, reducing the bitrate is becoming more and more important for emerging markets and flaky networks in general. We know that parametric coders, they can operate at very low rate, however, with very poor quality. That is until recently, where we can ask ourselves, can we build better parametric coders nowadays? And the answer is yes. We can use the modern deep learning techniques to model the data distribution and use neural networks to generate speech. Deep neural networks, they have shown very successful for speech processing in general, such as speech synthesis. One of the first neural so-called autoregressive models was WaveNet from DeepMind. It was an impressive system producing remarkably high quality speech. The drawback was that it came with very high complexity. With that high complexity, it was only feasible to use for cloud computing, where you have these big data centers full of computing powers. And WaveNet was designed for text-to-speech. And if we look at speech coding, there are some major differences between text-to-speech and parametric coding. First of all, the features that we use for coding are coming directly from real speech. So you have to have a speech analysis of the signal and not to generate these features from text. A more crucial difference is that text-to-speech typically has one or a small set of speakers that you know in advance and you design for, and you can only produce speech that sounds like those. We want a speech coding system where anyone can actually talk, and not only for a few designated speakers. So we set out to do a little research experiment to investigate whether WaveNet synthesis could be used for parametric speech coding. We took an open source low bitrate speech coder on the internet called Codec 2. It operates at 2.4 kilobits per second, and we used that coder to kind of control WaveNet for synthesis. So basically, we take the encoder part of this low bitrate coder, and instead of using Codec 2's own decoder, we drive a WaveNet with these encoded features from the encoder to get another type of synthesis. And how does this sound? Yeah, we did a listening test to assess the quality of this new codec. And the results are here. We can actually listen to it. If we just listen to the input speech, the original sounds like this.
Under terms previously reported, the Italian agricultural concern assumed about $195 million in subordinated debt as part of the transaction.
In its original shape, that's about 256 kilobits per second. If we now take a Codec 2 encoder and Codec 2 decoder, this low bitrate speech coder at 2.4, it will sound like this.
Under terms previously reported, the Italian agricultural concern assumed about $195 million in subordinated debt as part of the transaction.
And now we take the same encoder again, but now we use WaveNet to use as a synthesizer and a decoder.
Under terms previously reported, the Italian agricultural concern assumed about $195 million in subordinated debt as part of the transaction.
And as you hear, it's much, much better. It's actually very close to something running at maybe almost 10 times the bitrate.
Under terms previously reported, the Italian agricultural concern assumed about $195 million in subordinated debt as part of the transaction.
Okay, this was just a proof of concept with super high complexity. To make a practical speech coder, there are two major issues to address compared to the earlier experiments I just played out. First, you need sufficiently low complexity to put it on a device like a phone, and WaveNet is too complex for anything practical. Luckily, there are newer methods after WaveNet came out that are significantly less complex, so we can try to look at those. Another issue is that we have to be robust to different conditions. In a real situation, you have hardware and internal processing on your phone or your computer that will impact the audio quality. Also, the microphone will not only capture speech, there will be other types of audio captured, like background noise, sometimes other people in the room, and maybe even some music in the background. And WaveNet and neural synthesis systems in general are very good at modeling and reproducing a single source, such as clean speech, and they have been shown to be very good at clean speech. Let's happen what happens when the signal is not clean speech. And typically in a phone call, you will have some background noise and you will be in a room. So now we're going to listen to original sound from like a noisy and reverberated speech.
At NEC, the need for international managers will keep rising.
It's not so hard to hear what I'm saying. Well, that's a very typical signal in a phone call. And here is how the WaveNet coder tries to mimic that.
NEC, the need for international
So it doesn't have the vocabulary. It can only make speech sounds. So it listens and hear all these different sounds, and it tries to mimic it with the kind of arsenal it has, which is just speech sound. Here is an example of music. We can play music clip. Yeah, we don't need to hear the entire thing, and we can hear now how WaveNet is trying to play music. Yeah, we don't need to hear all of that either. So we have some work to do, and it took us some time to do that. Here's an effort to build a practical coder. In the previous slide, we saw that there are two major issues to address. First, complexity. We replaced WaveNet with a more efficient system. We selected one called GRU, which is a recurrent network. Secondly, we had sparse model for the matrices in this recursive structure, so we didn't have to do so many multiplications. And finally, we added some multi-rate processing so that we could generate a bunch of samples simultaneously. To handle many types of different input signals, we used MEL spectral features. They are rich enough to capture more than speech sounds. We also penalized unwanted noisiness when we trained these networks. And the result of this effort is what we call Lyra version 1. It was open sourced last year, and you can find the codec library at GitHub. Since Lyra version 1, we have experimented with a completely new neural engine. This time, we use an autoencoder architecture where we do end-to-end training of the encoder, the quantizer, and the decoder jointly. This is so-called non-generative, and we generate all samples in a frame at the same time. We train this system with GAN losses and other losses. The paper was presented earlier last year in a journal. Let me just first summarize the performance of SoundStream. I'll talk more about it in upcoming slides. SoundStream outperforms standard codecs for clean speech, noisy speech, reverberant speech, and also for some music, using up to about 4 times fewer bits. And it's scalable in the sense that we can train one model and then use this model for different bit rates. The complexity is very low. It can run real time on a smartphone CPU. And we can also build in denoising, so we can clean up the signal at the same time. We compared SoundStream to other codecs at 3 bit ranges. Here we call them low, medium, and high bitrate. Although it's only relative. It's not very high bitrate. And here you can see the results from a listening test. We can see that SoundStream, or Lyra version 2 as we will call it, is much better than our previous version 1 at 3 kilobits per second. It's slightly better than Opus at 12, and is approximately the same at EVS at 9.6. Opus and EVS are standard codecs used in conferencing. Let's look a little bit into the different types of signal that we used in the listening test. Lyra version 1 does very well on clean speech, pretty well on noisy speech, but fails miserably for music, which we heard before, that these type of generative codecs are pretty bad at that. Well, let's listen to how they sound. So we have now, the original here should be a bit noisy. Here is the reference, the input signal.
Mr. Jameson called the hospital.
Here is Opus at 6 kilobits per second.
Mr. Jameson called the hospital.
Here is Lyra at 3 kilobits per second.
Mr. Jameson called the hospital.
Here is SoundStream at 3 kilobits per second.
Mr. Jameson called the hospital.
And you can compare that to Opus at 12 kilobits per second.
Mr. Jameson called the hospital.
Here is what we call medium rate. At medium rate, SoundStream at 6 kilobits per second is approximately comparable to Opus at 16 kilobits per second. And it's also comparable to EVS at 13. Again, we gain a lot in bitrate. Here's the high bitrate results. High, again, meaning high rate relative to the previous ones. And in this scenario, SoundStream at 12 is approximately the same as Opus at 20. SoundStream at 12 is approximately also as good as EVS at 16. We can listen to this time mono music. We don't need to listen to the original, but we can listen to how the different codec versions sound. So Opus at 12. EVS at 16. And SoundStream at 12. Furthermore, can we do more than compression? Can we actually do compression and enhancement at the same time, try to clean up the background? The question is that, and the answer is yes, we can. We can let the system train with or without denoising. So when we train the system, we have the original signal that is noisy. We can try to make our best to mimic that one, but we can also train the system with a clean signal. So we learn how to clean up at the same time as we learn how to convey the information. And we can do during the training. We just tell it to should we clean or not, denoise, yes or no. And here you can hear the result of that. Here's the original with a little bit of noise.
Goods remains and is carried on by the...
That's the original noisy signal. Here's the target if we want to clean it up. It's a clean speech signal.
Goods remains and is carried on by the...
And here is if we use SoundStream where we don't denoise, where we actually just try to make the noisy sound.
Goods remains and is carried on by the...
And here is with denoising on.
Goods remains and is carried on by the...
And these are at 6 kilobits per second. So let's summarize what I talked about. Neural systems, these new AI systems, they are very impressive for such specific source types, such as clean speech. This is great for low-rate speech coding. They are not yet fully mature for general audio coding, but as you heard in the last slide, we're getting there. And that concludes my talk. Thank you so much.